It has often been said that it is important to look beneath the surface in order to gain a proper understanding of a subject. While this is likely the usual case, there are certain occasions where the surface itself may warrant a closer look. There are a multitude of miniature worlds hidden away within the more mundane world we are familiar with. Countless microhabitats, each with its own distinctive collection of residents. For various reasons, the laws of physics work a little differently at smaller sizes. Thus, many of these little hidden worlds are a good deal stranger and more alien than one might at first expect. Often, such places are hidden away in plain sight. One especially clear example of this is the strange interface of water and air. Every time we look at a pond or a lake or a river or a stream, or gaze out over the sea, we are staring right at this curious surface. Because of water's unusual properties, the boundary between water and air has some especially unusual physics, which become particularly significant at smaller sizes. This rather singular habitat can be difficult to live in, yet there are many forms of life that have become specialized to inhabit such a place. These include plants and animals, and a surprising number of microbes. The so-called surface microlayer includes a complicated microbial community quite distinct from the water just a short distance below. Whatever these surface specialists might be, they are collectively known as Neuston, or sometimes Plouston. These Neuston communities are too widespread and varied to properly address all at once. The ocean surface in particular has a wide variety of specialist organisms. So, for the sake of sanity and some semblance of brevity, let us focus on just a small fraction of what is actually out there. For today, we will confine our considerations to freshwater environments. Furthermore, rather than an exhaustive investigation, I believe it may be best to focus on just a few representative groups. A handful of specialist types of organism to illustrate some of the variations on life between air and water. Before addressing the resident creatures, I should take some time to explain some of the unusual physics of the water-air boundary. Likely the most important phenomenon here is surface tension. For the sake of simplicity, let us say that water molecules prefer other water molecules over air molecules. Now, a molecule of any sort is a bit too simple of a thing to have actual conscious preferences as humans understand the concept. However, the behavior of these molecules may be described using such terms as a sort of shorthand. It is not strictly accurate, but it is useful in conveying the overall picture in a manner that is relatively easy to comprehend. One might ask what keeps air and water from freely mixing. There are two basic differences keeping these two substances separate. One is the difference in phases. At the temperature range wherein water is a liquid, air is always a mixture of gases. The difference in density is considerable, leading to the most common arrangement of water being below air according to local gravity. The most mixing you ever see with water and air is dissolution in either direction, but even that is very limited. One might wonder why there is such limited dissolution. At least a partial answer might be found in the chemical differences between air and water. Air molecules are nonpolar mostly, that is, they have no difference in overall charge across their molecular structures. In contrast, water molecules are polar. There is an accumulation of negative charge around the oxygen atom in a water molecule, and accumulations of positive charge around the two hydrogen atoms. Polar and nonpolar molecules don't tend to mix. Now, water is not merely polar, it is extremely polar. Very few non-ionic substances can match the degree of charge separation one sees in a water molecule. This degree of polarity is sufficient for the formation of hydrogen bonds. These bonds are quite weak compared to the covalent bonds that hold molecules together, but they still exert a significant overall force. Hydrogen bonding is what makes water a liquid at room temperature. Without other factors, larger molecules tend to be liquid or solid at higher temperatures. Going by molecular weight, water weighs about 18 atomic mass units, and it becomes a gas at 100 degrees centigrade at sea level. In contrast, a molecule of oxygen gas weighs roughly 32 atomic mass units, while nitrogen gas weighs roughly 28 atomic mass units. Yet both of these substances remain gases until they are nearly minus 200 degrees centigrade. Such is the power of hydrogen bonding. Not surprisingly, such hydrogen bonds are powerful enough to confer noticeable physical properties with surface tension. As I said before, water prefers water over air. Where air and water meet, the water molecules at the boundary are only significantly attracted to other water molecules, so they are pulled with a net force down towards the rest of the water. This compresses the water at the surface. Surface molecules are more densely packed together, and in effect they are all trying to get closer to the water and further from the air. So here are the physics to keep in mind moving forward. First, air is far less dense than water. Second, water is very cohesive with itself and repelled by air. Third, this surface tension is functionally more significant at smaller sizes. So a small organism with a density between that of air and water, and at least partially hydrophobic coverings, will be able to stay at this surface pretty easily. With these physics in mind, let's look at just a few of the forms of life that call this surface home. First off, there is a small variety of floating plant commonly found in many freshwater bodies, particularly standing water. These plants are sometimes known as duckweeds in the subfamily Lemnoideae. A common and fairly representative species would be Lemna minor. These are tiny little plants, each consisting of a few leaves less than a centimeter across and a root descending up to a couple of centimeters into the water below. The leaves are covered by a waxy cuticle, repelling water and keeping them at the surface. They also contain air spaces in certain tissues, the parenchyma, so the plant is less dense than water and more dense than air. This physical property keeps the duckweed quite reliably at the water's surface. Incidentally, the root isn't especially waxy, so this keeps the plant firmly rooted in the water as well. As these sorts of physics work best at small size, the animals we see living at the surface also tend to be quite small. In freshwater, the arthropods are especially prevalent in this sort of niche. Part of the reason for this is their relatively modest size overall. In addition, like the duckweeds, they naturally produce a waxy waterproof covering over their exoskeletons regardless of their habitat. So it doesn't take much to adapt this wax to be a little more extensive. That being said, without sufficiently waxy adaptations, an insect that meets the water's surface may easily become trapped. Anybody who has ever dealt with an outdoor pool has likely seen this phenomenon quite a number of times. Still, with the right adaptations, many small arthropods can make a home on the water surface and often scavenge or prey upon their trapped cousins. Any creature that is small enough and waxy enough can effectively walk on the water. Such creatures are sometimes referred to as Neuston, as they exist just above the surface. Some of the smallest of these creatures are the collembolans, also known as springtails. These tiny hexapods are quite abundant on Earth, particularly in certain types of soil. However, there are a few species that appear to specialize in living on water surfaces. Two species of note are Podura aquatica and Sminthurides aquaticus. The former look like rounded approximations of an insect, appearing almost pudgy in overall outline. The latter are similarly globular with roughly spheroidal bodies and more or less spherical heads. As these creatures are so minuscule, they require no great structural modifications to remain on the surface. The waxy covering on their bodies is enough to keep them away from any danger of sinking, so they effectively make their way across the water's surface without any real difficulty. At their tiny size, it might be a little bit like walking on a giant trampoline. Generally, these collembolans scavenge over the surface, often feeding on microbes or the remains of trapped insects. In turn, they may sometimes become food for slightly larger sorts of Neuston. In freshwater, there are a surprising variety of water walkers in the insect infraorder Geromorpha. These are a subset of the order Hemiptera and include such creatures as the Valiidae, the Mesovaliidae, the Hydrometridae, and the Geridae. The Geridae, more commonly known as pond skaters or water striders, are perhaps the most highly adapted group for moving about on open water. As they are considerably larger than collembolans, some structural modifications are required to keep them above the surface. They are not merely waxy, but in fact have a covering of waxy hairs on their legs and undersides. These hydrofuge hairs make the water striders virtually unsinkable. Being caught out in the middle of a lake during a sudden rainstorm is merely an inconvenience for them, rather than a death sentence. These insects have 2 pairs of long, thin legs, the middle and back pair specifically, and these are the main locomotory appendages. The front pair of legs are shorter and tend to be tucked up beneath the creature's head. These shorter legs have small claws that are vaguely similar to what one might find on a praying mantis. They are used for much the same purpose. However, such would-be hunters need to locate their prey before they can subdue it with such weaponry, and the physical properties of their environment provide a unique means of doing so. As water is a liquid and air is a gas, and both liquids and gases are essentially fluid in nature, the interface between them is quite flexible. This flexible surface propagates waves very well, as anybody who has ever seen ripples in water can readily confirm. There are several sorts of arthropod, including the water striders, that use these waves in hunting. Any insect trapped at the water's surface gives off ripples as it struggles to free itself. When a water strider detects ripples from struggling prey, it will quickly move towards the hapless creature. The struggling insect is taken in the clawed limbs, and the bug's mouthparts are brought out. Like other insects in the order Hemiptera, the water striders have mouthparts modified into a piercing, sucking structure, allowing them to feed on the bodily fluids of the creatures they capture. The most extreme example of a water strider is found in the genus Holobates. These particular water striders skate across the surface of the open ocean, and they have a remarkably heavy coating of wax hairs over their entire bodies. While some creatures walk over the water's surface, others hang suspended just beneath it. The most common example would probably be the larvae and pupae of mosquitoes. Larvae have a siphon at the back of their body, while pupae have a pair of lobes, often called trumpets, extending from their thorax. The ends of these structures are waxy and hydrophobic, holding them above the water's surface and putting them in contact with air. In addition to this breathing mechanism, mosquito larvae also tend to have gills located near the base of the siphon, allowing them to breathe water directly to some degree. These larvae and pupae, like all other insects, have a system of air tubes within the body. The siphons and trumpets connect this air tube system to the atmosphere above the water. Though these creatures can swim down to evade predators, they tend to resurface after a short while and spend almost all of their time effectively hanging from the surface. When the larvae dive, a series of hydrofuge hairs around the siphon prevent water from entering the internal air tubes. These hairs also allow for an easy reconnection with the atmosphere as soon as the larva returns to the surface. In some species, though not all by any means, the eggs are also laid on the water's surface. When the mosquito emerges from its pupal stage, it emerges into the air, and it is light enough and hydrophobic enough to stand on the water's surface before flying away. There is at least one group of insects that lives neither above the surface nor below it. These creatures are pretty much at the surface, with half of their bodies above and half beneath. These are the Gyrinidae, often called whirligig beetles. While they can dive beneath the water or take to the air, they spend most of their time effectively within the water's surface. Their backs are typically above the water, while their undersides are submerged. The middle and hind legs are highly modified into short, stout paddles that can move the beetle with surprising speed. The front legs are relatively long and thin and capable of grasping prey. The senses of these beetles are particularly well adapted to their unusual habitat. The antennae are relatively short and thick and tend to be held right at the water's surface. They are capable of sensing ripples from potential prey, but they can also sense ripples from nearby gyrinids. These beetles are often quite sociable, clustering together in groups on the water, and they appear to engage in some degree of communication using water ripples. Perhaps the most unusual feature of these beetles is their eyes. They have 4 compound eyes rather than the usual 2 found in most insects. One pair of eyes is above the water, while the other pair is below the water. This is fairly important, as potential threats may approach from either above or below. After all, the water's surface is fairly exposed without many hiding places. Given such potential for predation, it should perhaps be no surprise that the gyrinids have a few defenses. Their clustering behavior may be a defensive measure in itself, similar to what is often seen in flocks of birds or schools of fish. Beyond this, these beetles often secrete defensive chemicals when disturbed. One of the most common of these is an aldehyde known as gyrinidal. It has sometimes been described as having a vaguely fruity odor, based upon the accounts of people who have handled gyrinids. I should perhaps at least mention the larval stage of these beetles. Unlike the adults, the larvae are entirely aquatic and tend to live at the bottom of whatever stream or pond the beetles inhabit. They have piercing mouthparts, not unlike those found in some of the Neuroptera, and they can be quite effective little predators in their own right. There are a great many other forms of life that also live at the boundary between water and air. As such, this has been only a brief look into this everyday little alien realm and its curious inhabitants. Still, it should suffice as a suitable introduction at the very least. Thank you for listening, and I hope you have enjoyed today's little foray into the unknown. If you are still curious and wish to venture a little further, here are a few things you might consider looking into. If you found this video enjoyable, do feel free to leave a like. If you believe others might enjoy it, by all means, share. If you wish to see more of this channel, a subscription should prove quite helpful. Until next time.